Over the past century, talks of melting glacier ice have become more and more prominent. Discussions center on how glacial ice melts, and this phenomenon, which can be seen through historical depictions of glacial ice, has been raising concerns over how the salinity of the ocean is contributing to iceberg and glacier melt. Now, contrary to popular belief, salt doesn't melt ice directly. Instead, salt prevents the water molecules from forming solid ice crystals, which lowers the freezing point of ice. And according to Scientific American, it's also important that the salt must be in a solution with liquid water in order for this principle to be obeyed. That's why many cities spray a salt solution before any ice forms. However, this phenomenon seems to be referring to the effect of adding salt to prevent ice in cities. I wanted to know how ice melts differently in saline solutions and how that could impact us on a global scale. This led me to question, does the salinity of water affect the rate of ice melt? If so, how? Well, as it turns out, I'm not the first person to ask this question. Many articles on scientific blogs and journals have attempted to answer this exact question to varying degrees of success. However, in a majority of the sources, it is determined that the ice in a fresh solution melts faster than a salt solution, but their certainty is questionable. In one case, the answer was to suggest performing an experiment yourself, while in other cases, the answer was even later determined to be incorrect. These questions were all posted to expert forums hosted by credible university doctorates, and the uncertainty in their statements prompted me to explore further. In particular, I found that a majority of the articles focused on the idea of thermal conductivity. But what exactly is thermal conductivity? Well, according to the Physics 100 textbook, conduction is heat transfer through stationary matter by physical contact, and thermal conductivity is the property of a material describing its ability to conduct heat. Consequently, simulations and experiments have shown that by increasing the salinity of a solution, its resulting thermal conductivity decreases. Then, is this it? Does that answer the question? Well, not so fast. You see, water is almost never stationary. As it cools down, it gets denser and falls away from the ice, so warm water can flow in without the heat flowing through the cold water. The answer seems to be density, as salt water changes in density a bit faster as it cools down than fresh water, which means it might move faster when you put the ice cube in, which helps melt the ice. However, it is also more viscous, so it's harder, which makes it harder to move, which slows down the melting process. These contradictory statements make the answer more confusing. So I suppose it's best to follow what the experts say and perform an experiment ourselves. In this experiment, we will be adapting the procedures proposed in a post on the Physics Stack Exchange forum. We will keep the temperature, size of initial ice, solution of water, and size of container constant, while changing the salinity of the water solution to see if the speed of ice melt also changes. I start with 2 labeled glasses filled with boiled deionized water to limit the amount of dissolved ions. Then I add 1 tablespoon of salt in 1 glass and stir to completely dissolve. Next, I measure both the solutions to ensure that they are the same temperature, as temperature can affect the rate of ice melt. I finally drop 2 equal-sized blocks of ice with added dyes for better visualization. As you can see in the time-lapse, the ice on the left, which is in fresh water, is visibly melting faster than that on the right, which is the salt one. Let's turn to another angle for a better view. In this view, we can see the density phenomena clearly. As the ice in fresh water melts, cooler, more dense water flows down, which pushes the warmer, less dense water upwards, towards the ice, towards the surface, and further contributing to melt. While the ice in the salt solution maintains its cool water towards the surface, as salt solution is more dense. This results in the ice in fresh solution melting faster than the salt solution. Indeed, density is what causes ice to melt faster in the fresh solution than the salt solution. In fact, the increased viscosity actually further helps to keep the cold water afloat, which slows down the ice from melting. While some errors, including more precise measuring tools and more controlled environments, could be implemented, I would say this experiment has been successfully performed. In terms of the global impact of this experiment, the Department of Energy Education at the University of Calgary explains this quite well. Frigid, low-density freshwater stays at the surface of a lake or river, forming a layer of ice on the surface. Land ice differs from sea ice in the way that it is formed. Freshwater becomes less dense as it approaches the freezing point. In contrast, sea ice forms quite slowly compared to freshwater ice because the saline water tends to sink away from the cold surface before it's cool enough to solidify. Fortunately, there is more ice in contact with salt water than freshwater in the world, which means less ice would melt. This agrees with the experimental data we performed and shows that we don't have to worry as much regarding sea ice melting. However, that is not to say we shouldn't care about our diminishing glaciers. As our planet continues to get warmer and oceans continue to rise, it is the duty of every individual to protect this place we call home.